Hello everybody, let's take a look at section 7.2, which is where we're getting into looking at a survey and pulling samples from a population and making decisions about the population based on what we're seeing within those samples. So I want to start off with a little bit of vocabulary, and then I'm going to try to look at a simulation on the Art of Stats website that I think we've used a few times in class so far. If not, we'll be using it a little bit more in this unit. So make sure your cell phones are put away and you have your notes out and you're ready to go. So a couple general points to start off. So statisticians evaluate the method used for a survey, not necessarily the results that they get. Obviously the results are important, but what we're interested in when we're evaluating how good those results are, how meaningful those results are, is how was the survey conducted, the method, where their bias is, was the sample large enough, things like that. The goal is to be accurate and precise. That's what we want. That's ultimately our goal. Accurate, we get accuracy by reducing biases. The less bias we have, or our goal is to be unbiased, that gives us accurate results, meaning the method measured what it was intended to measure. It correctly estimates the population parameter. If my goal was to estimate what proportion of citizens voted, we're going to vote for a candidate in an election, and then when the election was over, we looked at, okay, how accurate was our survey? Was it close to what happened in the real election? That would be our population proportion. So is it accurate? Does it measure what we needed it to measure? Is it precise? So in other words, if the method were to be repeated, if we were to do this again and again, the estimates are very close, or let me use the word consistent. I think I like that better. The estimates are consistent. There's not a lot of variance. That's our goal. And so just a little graphic here to kind of drive home this point. This is what we want, accurate and precision. So it's at the bullseye, and the little dots around it you can see are very close to each other. There's not a lot of variation. Here's one that's not accurate, but it's still precise because the dots are close together. Here's one that's accurate. It's fairly close to the target, but notice it's not precise because the dots are all over the place. And here's this one that's not accurate or precise. So what is a sampling distribution? That's what we're going to get into in the next couple of chapters, and this is really an important point. What do we mean by a sampling distribution? Well, remember what we're doing. We're taking a sample from a population, and we're using information from that sample to make an inference about the population. So samples may be used to make inferences about the population. The idea, though, is that if we were to repeatedly take samples from the population, and I say usually in theory, if I were to take sample over and over again from the population an infinite number of times, then that creates what's called a sampling distribution. And this sampling distribution has some really key characteristics that will help us make inferences about the population. It will help us decide how good our survey is, how well our sampling method has worked or is working, and give us some estimates for what we think will be true about the population. So let's look at some of those characteristics. And I am going to switch over to the Art of Stats menu. Let me pull up the website. Hang on one second. All right, I've got the Art of Stats website pulled up, and we're looking at a sampling distribution. And let's just you don't have to write anything down here, just kind of watch for a couple minutes. What we're doing here is we're saying, all right, the population, we're going to say we're assuming the population proportion is 0.7. That's the number we're going with. So notice P equals 0.7. What I'm going to do here is I'm going to pull random samples, and I'm going to start with size 10 from this population. And I want you to look at the sampling distribution that's created. So I'm going to pull, there's one sample, and you can see in my sample, P hat is 0.8 this time. Sample size is 10, P hat is 0.8. I'm going to pull another sample, and in my next sample, P hat was 0.7, the same as the population. The mean for those two that I've just pulled is 0.75. Think about that. I had one that was 0.8 and then one that was 0.7. So if I average those together, I get 0.75. I'm going to keep on pulling samples here, and I'm going to pull 100 samples at a time. So here's another one. All right, I'm going to do another 100 samples. And what I want you to notice, this graph down here in blue, that's called our sampling distribution. The population proportion was 0.7. Keep that idea in mind. That's what's with that little orange semicircle right there. My sampling distribution, however, has its own mean. And that mean that the computer's telling me is 0.694. That's pretty close to 0.7, isn't it? So the more samples I draw, notice it fluctuates. It dances around a little bit, 0.699. I'm going to just keep drawing samples, but it's pretty close to 0.7. It stays pretty close. And the reason that's happening is because I'm drawing random samples. So let me go back to my notes for just a moment, and let's write that down. So where it says the estimator p hat, it's going to be unbiased as long as we take random samples. So p hat should be roughly close to p, whatever the population proportion is, so long as we're selecting random samples. Now let's talk about the shape of the sampling distribution. So in my picture here, I was only pulling samples of size 10. Don't forget, remember n was 10. And you can see there's quite a bit of spread here. We've got a lot of spread. This graph has a lot of holes in it almost, you could say, but it's pretty spread out. I'm going to increase my sample size. I'm going to reset this, and I'm going to increase my sample size to, let's say 50. And I'm going to draw 100 samples at a time again. And there's my graph right now. So here's 100 simulations, size 50 each. Notice my mean again is 0.69, very close to the population proportion of 0.7. And we'll come back to the standard deviation in a second, but what I want you to notice now is that the graph has less spread. Do you see that? It wasn't nearly as spread out as the previous graph. Here it is again with another 100 samples. And then here it is again. And then again, I'm going to keep drawing samples. And I want you to observe that the larger my sample size is, the closer I get to a normal distribution, and the smaller the spread. Let me increase this to sample size 100. I'm going to reset it, and let's do it again. Here it is again. Now we have sample size 100. Notice that it's a little bit closer to a symmetric or a normal distribution, but the bigger thing I want you to notice is that the spread is much, much smaller, right? This graph is a lot more compact than the one that I started with. So let's put that in our notes and let's kind of summarize what we're talking about here. The shape of the sampling distribution is going to be more symmetric as n, the sample size, increases. And then the last little point I want to make here is that the precision improves. So in other words, precision, remember, was consistency. We can think of that as spread. So the precision improves, the spread gets smaller. That's our goal, right? We want less spread in our graph. The spread gets smaller as n increases. So the larger the sample, the better our precision. There's a special name for that, and that is called the standard error. And we're going to talk a little bit more about that down here. The standard error is a fancy way of saying the standard deviation for that sampling distribution that we just created. So a couple things to note here. The bias of p hat is going to be 0 as long as we take random samples. And the standard error, so the formula for the standard error, so that's this number right here, is going to be given by this little formula. It's the square root of p times 1 minus p divided by n. And let me go back to the artostats for just a moment. And let me just show you how that relates to what we're doing. Now, I don't think I can write on this website. It's not going to let me do it. But notice right here, jot this down, 0.444, and I did sample size of 100, and P was 0.7. Keep that in mind. So for this distribution, my standard error would have been 0.7 times 1 minus 0.7 divided by 100. And I want you to pause the video and I want you to put that into your calculator and tell me what that gives you. And I'm getting approximately 0.04582. And what I want you to notice is it's a little bit different, but it's close to this number right here. The reason this number is slightly different is because it varies with every sampling distribution. Every sample is different, so every sampling distribution is going to be different. If I keep drawing simulations, this number should, in theory, get closer and closer to this number. But this is what the standard error should be for that particular sampling distribution, so long as two conditions are met. First is that the sample is random, which ours always will be, so you don't have to worry about that, and that the population is at least 10 times larger than your sample size. So if you're talking about like the population of all voters in a district, for example, population certainly is going to be large enough. So that one is not as important, but the randomness, I mean, it's important, don't get me wrong, but it's, in our case, it will always be the case. The randomness, though, is also very, very important, and we're going to assume that we're working with random samples whenever we're looking at this data. So I know this is a lot. This is a little bit confusing. This is a really difficult topic. So just come to class tomorrow. Make sure you bring your notes with you. And what we'll do is we'll do some more simulations looking at these sampling distributions to kind of get a feel for what we're talking about. So I'll see you then.